morning, student. The continuation of Unit 1, Electrostatics. Now go moves on electric field. You know Coulombs Law. The Coulombs Law is explained the force between two charges. So one is whether it is a attraction force or repulsive force in between two charges. You know, like charges are repel and unlike charges are attract. How will you two charges are attract or repulsive? If one charge is a stationary, or another charge moves towards that one charge, stationary charge, then only it will reflect or attract. So this charge, the stationary charge having some field. So the another charge enter this field, then only the charge may reflect or attract. So the charge of any charge having some field around it, this is called a electric field. So the electric field is defined as the space around the charges is called electric field. So the electric field, the concept is first given by Michael Faraday. He only explained the concept of electric field because the interaction between two charges, if all charges having some field around it, then only it will attract or repulsive to each other. So let us consider the charge Q are placed at a point of A. Now charge Q naught is at the point of B. The charge Q is a stationary charge, Q naught is a test charge. So the electric field is the line joining the Q naught is E, that is electric field E. Now we want to calculate the electric field from the Coulombs law. You know the Coulombs force between Q and Q naught, F is equal to K into Q naught by R square into R cap. You know already the K is a constant proportionality, Q is the one of the charges, Q naught is a test charge, R is the distance between these two charges, R cap is a unit vector. So rewrite this equation, F is equal to 1 by 4 pi epsilon naught Q naught R square into R cap, just substituting the value of K, where the K is 1 by 4 pi epsilon naught. Now the electric field, already know that is a space around the charge. How will you define the electric field? That means the electric field is defined as force experienced by a unit test charge. For example, is a charge Q. This charge having some field, that is called a electric field. If another one charge kept here, there is no any interaction, but kept inside this having some interaction. So the one charge kept another charge of electric field, then only the charge are attractive or repulse. So some force is experienced on this charge, that is called a electric field. Now the electric field is defined, the force experienced by a unit charge. The force experienced by the unit charge is called electric field. So the electric field is expressed by E is equal to F by Q naught. That is force experienced by unit test charge. Charge means test. That is a test charge. So E is equal to F by Q naught. Here substituting the force value, So 1 by 4 pi epsilon naught q naught by r square in this q naught. So the q naught will be cancelled. Rearrange this equation. E vector is equal to 1 by 4 pi epsilon naught q by r square into r cap. That is expression for electric field due to a point charge. Now the electric field is a vector quantity. The unit of electric field Newton per Coulomb or Newton Coulomb minus 1. This unit will comes from electric field formula. So force, unit of force Newton, then charge Coulomb. So Newton per Coulomb or Newton Coulomb minus 1. Okay, we learn next chapter electric potential. So here electric field E is equal to V by D, this formula volt per meter. So the electric field or electric field intensity, having two units. One is a Newton per Coulomb or volt per meter. So the electric field intensity expressed by both units, Newton per Coulomb and volt per meter. If the Q is a positive charge, then the electric field points away from the source. If the Q is negative, the electric field points towards the source. So already informed that if the positive charge, the electric field outward. If the charge is negative, the electric field is inward. So we want to calculate the force of the electric field. Just rearranging this equation, F is equal to Q naught into E. That is force experienced by the unit test charge inside the electric field. Now next one, the electric field is independent of the test charge and it depends only on the source of charge. Here the electric field depends upon only this charge, is not depends upon the test charge, that is a Q naught. The electric field around the any charge depends only the source of charge, does not depends upon the test charge. The electric field is classified into two types. One is a uniform electric field, another one is a non-uniform electric field. Whether the electric field said to be a uniform, all the points having the same electric field in this region. If any point A, B, C or consider any point having the electric field should be a same. It is said to be a uniform electric field. Another one, non-uniform electric field. The electric field is different for different points. So the electric field is said to be a non-uniform. That is called electric field. Have two types, the uniform and non-uniform electric field. Now we move on next one, electric field lines. How will you form the electric field around the charge? Is expressed by the electric field lines. Now consider a 2 point charges plus and minus Q, plus Q and minus Q is a charge from the lines of force around these charges have different ways. Now the Faraday explained the electric field lines is imaginary, straight or curved lines from positive charge to negative charge. The electric field lines are straight or curved. Imaginary line is from positive charge and terminate to the negative charge. But the electric field lines we seen in the visualized in the help of charge and field. So some experiment having the visualized electric field. Now we see on the properties of electric field. First one, the electric field line starts from positive charge and end at the negative charge. The electric field lines is always starting from positive charge and terminate to the negative charge. When the electric field is, the charge is positive, the field lines radially outwards. When the charge is negative, the electric field lines radially inwards, because the electric field start from positive, so all are outward. The electric field lines terminate at the negative end, so all electric field are towards the negative charge. The electric field vector is a point in space is tangential to the electric field lines. We want to calculate the electric field vector at any point is a tangential to the electric field lines. So that is a tangential. If you want to calculate the electric field vector, it will be represented by one tangential. Next one, the electric field lines are more closer, so the electric field is large. See this area, the electric field lines are very close to each other. We see this area, the electric field lines are fair. So the electric field is very large when the electric field lines are closer. The electric field lines are far away, the electric field lines are lesser dense. So when the field are more closer, the electric field is large. The electric field lines are far away, the electric field is small. Next point, no two electric field lines intersect to each other. See here, this diagram, there is no any intersection of two lines. So the electric field lines do not intersect to each other. There is not possibility to crossing the electric field between the positive and negative. If two lines cross at a point, then there will be a two different electric field vectors at the same point. When the electric field cross to each other, so the different electric field vectors at same point, so then maybe it is a possibility to cross the electric field. Then the number of electric field lines that emanate from the positive charge and end at the negative charge is directly proportional to the magnitude of charges. When the electric field is very strong or the electric field is very weak, depends only the magnitude of charges. And the charge is, one charge is 2 coulomb, another charge is 5 coulomb. Which charge produce a more electric field? Already known is a magnitude is large, 5 coulomb. So the electric field is strong. Compare the 2 coulomb. So when the electric field is large or small, their magnitude depends upon the magnitude of charge. We move on. Electric dipole. An electric dipole means two equal unlike charges separated by a very small distance is constitute a electric dipole. Now see here, minus q and plus q, two equal and opposite charges are separated by a very small distance. So the distance between minus q and plus q is 2a. See, the two equal and opposite charges separated by a small distance constitute an electric dipole. We have the two types of dipoles. One is a dipole. If any dipole, the centers of the positive and negative charges do not coincide to each other, such a molecules behave as a permanent dipoles. See, the center of the positive charges, center of the negative charge do not coincide. If coincide means it's not a dipole. So the positive charge, one molecules having a positive charge and the negative charges are separated by a very small distance, then only to constitute a dipole. Otherwise it's not considered as a dipole. So now for example, carbon monoxide, H2O, ammonia, HCl, all are dipole molecules. For a H2O, see form HOH. Here H is a positive charge, oxygen negative is a positive charge. So the dipole form between hydrogen oxygen molecules. Here another one dipole form a minus plus, that is oxygen and hydrogen. So the water molecules act as a dipole. Now another one related to the electric dipole is electric dipole moment is always represented by P. See here negative charge at a point of A and positive charge at the point of B. The distance between these two charges is 2A, is divided by 2 vector notation, is a y direction, is a x direction, but the minus q and the plus q are along the x direction. Now from this, the electric dipole moment is defined the product of the one of the charges and distance between these two charges. The dipole moment is defined as the product of one of the charges and distance between these two charges is called dipole moment. See the dipole moment here is a positive charge is always higher electric field than the negative charge. So the electric dipole moment P is equal to Q plus Q, or plus vector minus Q or minus vector. Here plus Q is a more electric field than the negative charge. So the R plus vector, position vector of the plus Q from this origin, that means this is considered as the origin. This is a position vector from the minus Q, this is a position vector from the plus Q. So R minus the position vector of minus Q from this origin. So let us consider the origin is here. So from the minus Q is there is a R minus, or position vector of plus Q, that is a R plus. So from there the Q AI minus Q A of minus I. Q one of, because the from definition the product of one of the charges is a plus Q. The distance between the origin A, I is a position vector because the dipole moment along the x direction, minus Q, the distance A, the position vector minus I, because it's a direction of electric dipole moment. So the minus Q is opposite direction, so put the minus I is a x minus x, I minus I. So the minus Q will represent the position vector is minus I. So the resultant become 2QA I vector. The I vector represent the position of dipole moment. Here the position of dipole moment along the x direction, then only we put the I cap. So the dipole moment P is equal to Q into 2A. Come from the definition, product of one of the charges and distance between these two charges. So P is equal to Q into 2A. So the dipole moment is always act from minus Q2 plus Q. If any material, for example carbon monoxide, any molecules, carbon monoxide, H2O, ammonia, HCl, hydrochloric acid, of any molecules, the dipole moment act from minus Q2 plus Q. The dipole moment is a vector quantity. The unit of dipole moment is Coulomb meter. The unit Coulomb meter derived from this formula, P is equal to Q into 2A. The unit charge Coulomb, 2A distance meter, that is a Coulomb meter. So now the dipole moment is always act from minus Q to plus Q along the electric field. Now we move on. The electric field due to a electric dipole. So you know the dipole and dipole moment. Dipole is a two equal and opposite charges separated by a very small distance, and dipole moment, the product of one of the charges and distance between them. We want to calculate the electric field due to a dipole. Having these two cases, first one, the electric field due to an electric dipole at a point on the axial line. Next one, the electric field due to an electric dipole at a point on the equatorial line. So now move on. See first one, axial line. The electric field due to the dipole. Now see the diagram. The minus Q placed at the point of A and plus Q kept at the point of B. The distance between these two charges is a 2A, and from the origin minus Q is A, from the origin plus Q is A. So the dipole moment P acting along the minus Q to plus Q. Now we want to calculate the electric field at the point C along the electric field. So the point C placed at the distance of R from the origin O, that means the center of the dipole. So we want to calculate the electric field E d2 plus Q and electric field E d2 minus Q. The charge positive, the positive charge is always the electric field directed outward. That's why the electric field direction E plus. The electric field d to the minus Q always towards. So E minus towards the direction of minus Q. Now we want to calculate the total electric field at the point C. Now the electric field at a point C d to the plus Q is, on the electric field at a point C d2 plus Q is E plus is equal to 1 by 4 pi epsilon naught Q divided by R minus A whole square along the BC. This formula comes from, you know the formula of electric field, 1 by 4 pi epsilon naught Q by R square. It's a common formula for electric field. Now we want to calculate the electric field on the C, d2 plus Q and d2 minus Q. Now we written the first one, E plus Q. The charge plus Q, the point up to the distance of C. Here is a, want to calculate this one. So here from origin to C is R. This is a. We want to calculate the plus Q to Z, just R minus A. We want to obtain the distance of plus Q to C. So R minus A whole square. So rewritten this equation, E plus is equal to 1 by 4 pi epsilon naught Q by R minus A whole square. The along the BC is along the direction of dipole moment vector P. So the P vector is electric dipole moment unit vector from minus Q to plus Q. Now we want to write electric field at a point C d to the minus Q is E minus is equal to minus of 1 by 4 pi epsilon naught Q by R plus A whole square. Here plus minus represent the charge of minus Q, and here we want to calculate from A to C. So up to OC R, here is A, so the total distance is R plus A whole square. Now we see, because the electric field at a plus Q is more stronger than the electric field at the minus Q. So the electric field E plus is stronger than the E minus. From the superposition principle, we want to calculate the total electric field at the point C. E total is equal to E plus of E minus. So substituting the value of E plus 1 by 4 pi epsilon naught Q by R minus A whole square P cap minus 1 by 4 pi epsilon naught Q by R plus A whole square into P cap. We taken out the common terms Q by 4 pi epsilon naught, remaining we get 1 by R minus A whole square minus of 1 by R plus A whole square into P cap. Now same written Q by 4 pi epsilon naught here. In the cross multiplication, we get R square minus A square whole square R plus A whole square minus R minus A whole square. We expanding this equation A plus B whole square, we get Q by 4 pi epsilon naught R square plus A square plus 2 RA minus multiplication R square minus A square plus 2 RA by R square minus A square whole square. Rearranging this equation, cancel R square, A square, we get 2RA plus 2RA. So E total is equal to Q by 4 pi epsilon naught 4RA by R square minus A square whole square into P cap. Here compare because the two charges in between is very small distance. A is a very small distance, compare the R. So R is greater than A, or A is very less than, compare the R. So just neglecting this value, under the condition of R is greater than A, R square minus A square whole square, this cancel this small value, we get R power 4. So the R square minus A square whole square nearly equal to R power 4. Substituting this value for this equation, E total is equal to Q by 4 pi epsilon naught 4 RA by R power 4 into P cap. This equation E total is equal to same, we written Q by 4 pi epsilon naught, separate this equation 2 into 2 RA. So R and R power 4 cancel, we get E total is equal to 1 by 4 pi epsilon naught 2Q 2A into R cube by P cap. Here 2A into Q or Q into 2A, we know that dipole moment P. So instead of this, we written as a dipole moment. So finally we come E total is equal to 1 by 4 pi epsilon naught 2P by R cube. That is the electric field along the axial line. Here the electric field acting along the direction of dipole moment, because the dipole moment is always act from minus Q to plus Q, that is the direction of dipole moment. So the total electric field acting along this direction, that is the dipole moment direction.